let's see. Yeah. So we here we were looking for this address. To start from the start, we have the C program here with a pointer to function buffer. It says FP to 0. It gets something into the buffer. This is where we can do a buffer overflow and input too much data, so we overwrite this one too. And if this is if this is still 0, it won't try and call something. But if it has been set to something, it first says the address. Here, the FP in this format. And then it calls the function. And yesterday, I guess it was, we tried first running it, seeing what. Yeah, so we inputted hello, then we get no output back. Then we put in, since we know it's 64 characters here in the buffer, so we put in 64, and then we put in, I think this is what we had before, so I just used the same. And this will be DCBA, right? Lowercase. And then, so to actually be more serious, let's hop to the right place here, and this one had, then it probably was number 1. Here, it wanted this 61, 62, 63, 64, and we kind of cheated here. Though we actually did it before. But this assembler of R2 here, you just run R2, D for debug, A for like analyzing. You can do 3 A's here instead after you get to its prompt. So we just PDF main, which means disassemble the function main here. And then we could see in clear text what it is, even in the sorted backwards order. A little endian order. And I also made a screenshot because it has so pretty colors that we lose when we just copy the text. And then, well, we did number 2, where we used a variable instead. There's a variable here, environment variable. So we set that instead. And we needed to get \r, \n/r twice into there. And we tried this, it doesn't work. And then we did it with Python instead, and then it worked. So we could get the right characters in this way. I also tried different versions of this here before, and then we're at number 3. So this we did yesterday. We have finished this one. We're supposed to continue with number 4. But I'm always repeating what I did last so that I remember and learn more from it. So I already explained this code, our test here, and then we tried with Python. I'm just typing here. We want to do this test different output, then let's pipe it instead. So it asks for the input, you know. You can like cheat and have it on the command line. You can just make a tiny change and run it again. So it's an easy way to test different things. But on my computer, the let's see, 61, 62, 63, 64. Right, so this actually got the right value, right? So we're on the right location in memory. So let's find the address we want to hop to. And we found the address here. by going to R2 again and running AFL to list the functions with their addresses. I think this is the number of times they're called, maybe, right? Anyway, we turn this inside out or backwards, rather. So I just put it here so it's easy to see. When here, it's just this. And then we run with Python again, turning it backwards. And when we run this, it says jumping to, and as you can see, it's not the right one. Well, it seems like the right one. Here, if you start at the, well, start or end, it has 24 here. Good. Then we have C2. Then we have the 8.4 and the 0.4. And this one is like pushed out of there. So this is on my modern Kali machine. So I'm assuming that this is a security feature because we checked. And this has worked for other people. This is a solution they have written down that works. So it's the same. And I see myself on my right screen, but we do have Kali here. And right, I'm probably on Hack the Box here. Right, since you're not supposed to show these boxes, I'm just hopping over and I can remove. So I have two terminal windows up here. And burp there, so now we can hop back. So this is the Protostar one. So here we have where we run it on this machine. We just tested it would work later on the other one, and yeah. Let's just see here. So as you can see, we tested adding more of these, and then we got 4.1, 4.1, 4.1, 4.1. So we can try this more times, see if we can manage. 4.1 is hex for a capital A. That's what we put a number of here. So, but I had to run. I had to go to train yesterday, so I had to run. I did time to not miss. Yeah, so to test this, I connected to a Try Hack Me box. By the way, that shouldn't be running. Let's connect there again. I'm thinking we will need this again. So right. So let's just scroll up a bit, because this is things that we want for our notes. So we connected to this Try Hack Me box that is intended. It has its own buffer overflow stuff, so it's set up not to be very secure in that area, right? So we have used it several times. Let's see here. Yeah, these overflow ones. So I copied the stack 3, the one we're looking at there, and it didn't work very well. So I instead just put the code there and compiled it with this. That's also in my notes that are public. That if you want to compile something to do buffer overflow and test stuff, you can use these. But we really should get more information on them. I know that I have like a bit of notes here. So the no FNO stack protector, remove canary stack cookies that TCC adds to make sure the stack was not tampered with. and the remove new PIE here. Position independent executable. Loads executable at a different memory address every time it's run. And when we're doing these tests, that could be like a mess, right? So, but I guess we'll need to learn how to cope with those too later. But for the first baby steps here on buffer overflow, we're just shitting. And that's also why we're running it on this like specific VM that's set up for this. We get a warning that gets is not safe. Shouldn't you use fgets instead? And it just warns us a lot about this. It's dangerous, should not be used. That's why we're testing it, because it's vulnerable. So I just listed them to make sure that the date updated here, and then we run it. Let's see. Right, we did R2 on it, because this didn't give any output. So I wanted to check stuff. Also, this was just a test, as you can see. This is not an address. So we wanted to find out on this machine what is the address for this. So we found that SimWin has this address. And then we just quit here. And then we were back at the prompt, and now we do this address here instead. Reversed. And it didn't work, so I did nano and checked, did I type this right? I compiled it again, the same result, you know. Then I did this again to double check that when we recompiled it, we still have here the same, and we did have the same. So then what could it be? We tried it again. Let's see, what did we do here for difference? Yeah, I added a lot. I did 640, I did 0. So we did get a segmentation fault here, which is what we would want. But it actually doesn't work. I mean, there's no security there, like fixing all the buffer overflows. So it's supposed to crash. Also, I added hello there at the if messages in the C code.
Josen44454 says
now we have another version here.
viewers on KJ2Z3G.SBS/E1AK.
So I'm very curious about these texts, you know. So did I save that notepad? No. Yeah. So this is one, and then we have this one. An H with this on top, right? This is not normal characters, so spam messages. There. So let's keep that one up. I'm not going to add it again to the deleted the message, so I'll have to do it manually until I have like a regex or something. But if it randomly removes some of the letters, messy. I guess they're doing that for a reason, right? They want to get through and get people to see the message. Yeah, so also we got the ace in there, right? And then I tried, let's not do this much, let's just do 70, and we kind of started to get there, right? We're just on the edge, half of it is there. So we just added 2, and we got hello there, calling function pointer, jumping to. Code flow successfully changed, so we managed to hop here to the win. And we have not documented this in our stack 3 notes, so we'll have to do this. And maybe I should change this too here. Check that this works with other people. not. So I was quickly just getting something here before I had to leave. Not on the original ISO VM. It's an ISO bootable. That was supposed to run it since it has a US key. That's why. It's like I can't type there. Like, where could this key be? Maybe there, when you're trying to solve a problem. That's not fun, you know? Trying to learn things, focusing. We used the THM BUF1 rooms VM to compile and run the code. The ELF did not. It couldn't start. So anyone else? I just realized, rather, it doesn't disturb me, that there's a sound outside. Yeah, let's close the window. It's kind of persistent, right? I don't know what they're doing really. Let's see if we can see. I don't know. It's moving. So, quiet. So, close the window. It's just on the other side of the computer. So I used to like filter the sound, but it sounds so bad. When bits of my voice gets cut out, it's not nice. So I'll have to. It's kind of nice. It's 26 degrees in here. That's like my perfect temperature. I guess it will get hotter tonight though. Yeah, I can still hear the sound actually. So just checking that I do have audio on here. So we're going to copy some stuff over there, right? So maybe I should just get it all. We don't need the connection lost. Oh right, at the end here, I by mistake, you can see I pasted all of the above. So that's why we have so much stuff after here. This is not like a command, but it's at the prompt. So it's just get a lot of bash errors. That's funny. So this is the interesting bit here. So up to I'll cut off the words instead. So we did copy the file. There. Yeah, I think I copied it on here. We SCP'd it there. But I was already connected, so I didn't want to like hop out. Let's try again a bit on my machine to see if we can get this working actually. The more we dig in it, the more we'll learn, right? So this is just that the ELF didn't work. So here I think that I will skip a few of the messages. Like we don't. This might be interesting, right? So, and this is also a bit interesting. Then that we run it several times. Oh, that's funny. It removed this line from it. Yes, I was going to make a hop here. So we don't need to see that the file got there. We don't need that. We don't need... Let's see, we want to see the address. This R2 bit here we want to see. But the first bit here, I have just dotted because, you know, it's just a few information and warning messages. So what we're interested in this, we don't need to see the quit bit. So I'm actually going to again like just put a break there, so it's like clear that these are related but not exactly connected. I think it's easier to read. And then we tried this. So this line here, I'm going to put it underneath. Or rather, let's edit it. The when function is at dot. And then we have turned this address around. And since it didn't work, I was like, what? Let's add some error checking. I'm going to actually delete that part of the output so it doesn't matter. And we don't need this again. So this is the same output after I added the debug output, you see, right? It's just bugging here. I'm doing nano again, and then it's like bugging out the output. So these are not interesting. What is interesting is the change of type. So the calling function is the interesting bit, and the segment fault. And this is not interesting again. And this. I'm just removing what I edited in the code because it's not interesting. So this is how we there are a few extra bytes on this machine compared to the original image, but we can run it. So, and I misspelled machine again, and I'm like always thinking of it when I'm actually doing it, but this time I didn't stop, so my fingers do it. I'm not responsible for my fingers, am I? Oh, I don't have my water. I'll have to go get my water. Yeah, so before we abandon this one and go to the next one, I do want to give another test. We had the time limitation there, so we did this kind of quickly. So if we just run this again, we should get the same message, right? Well, let's see. So we have, we tried it with 72 here. And we got all the A's here. So I'm just, let's move my mouse somewhere. No? Click. Why can't I arrow up here? So if I mouse away. Okay, so if the mouse isn't over this, I can't do stuff. Eh? Is it just like clicking randomly? I don't know. So my hair is very, very flyy today. So let's decrease it with then. Well, actually, let's do 64 again. Let's do 63, right? To have something to compare to. So 08, 04, 84, C2. So I don't think we can get around this really. We're on the other end now compared to this one here, where we had the 2-4. So the C2 is in there. It is there. Let's look with R2 what it looks like, right? So R2 DA. Yeah, this is the command. This is what we want. And so AFL. And just to confirm that this is the address, 08248424, right? It has not changed. It is still what we have in our notes. Over here. Alright, it's still at the same place. So I'm like, how did I rerun it? OOD, arguments, right? But we're not going to do arguments. And we're not really running it either. We can step through it, I guess, right? And then we can look at the memory. So these are the notes for R2. We can do breakpoints with db sim main. I'm curious, do we need to do sim main? It's just main here. Sim win, but not main. So I think I just messed up a bit there. So db, like lots of stuff starts with D, but I guess B is breakpoint. Debug breakpoint maybe. That would be like debug continue, debug continue, debug step. That would be logical, right? When we want to print out the memory contents, we are not using D commands. And not with disassembly either. Though there's a D in here, but I guess that's for disassemble here, right? Disassemble function. Like print disassemble function, maybe? And here also print hex and the address. Maybe nothing more than that. This is annotated. Hex, yeah, hex dump. So print hex dump. Print hex dump. Annotated. The PXA one is the one that I'm using. I'm using this. Right. It seems nice because you can see where stuff is pointing to in the memory. That's nice. Very nice. So let's do it. That's what we're going for now, to see what's actually on the stack, how it looks. We don't have any graphical tools since this is a VM. Really, it's supposed to be a VM. I guess we could do it now. Yeah. So far, all the ones have been on VMs, and this is supposed to be on a VM, but it's actually on our local machine now. Oh, had to click extra time to get the Kali menu. Well, it's bugging sometimes. There, Kali menu, I can see you. So, EDB, I noticed this. I just went through here and was looking randomly for what tools we have. Oh. Okay. I should update later. Not now. So, right, it should be running, but it's running in debug mode. So let's open. And it's not buffer overflow we want. Oh, Kelly. So I don't remember what the name of this thing was. Vulnerable, right? Yeah, got it. And then we have stack 3. Oh my. It's so pretty. It's so pretty. And I made the size of the text bigger. This one didn't really work with bigger text, so I'll let it be tiny. Right. Isn't this wonderful? Yeah, I'm a bit like, yay, I love this, kind of, you know. Look, we can see where we are. It's paused on this instruction by default. So let's check this stack out here. We haven't really started the program yet. So what if we just step on step? Let's see what it is. So we don't want to run it. We don't have any breakpoints. So let's just step. So F7 and F8. So we don't want to do F7 on the calls. That would be bad. Here we have a call. This would be the gets, right? Which would be kind of like going through all of their code for getting the string. And we don't want that. So step over. Pause signal to application. So let's try a bit of F8. See how it works. So if I do F8 now, it hops down one step, and then it there, and we can see all the things. I'm in love. Look. So now we can see EAP here is on this line, also with a nice arrow. You can see the instruction is 50 or 50, push EAX. So EAX, well, let's see what happens when we do this, right? But first I need to like scroll here. So are there like columns I can control here? Because I have a bigger font, even though it's tiny. It's a bigger font, and I know you can't see all of it. But this is, yeah, maybe I should like hop myself somewhere else. What's the least interesting? This corner maybe? Because we want to see the stepping through the instructions, right? So I'm going to step one more step here. So Here we have the stack. If I scroll here, so these are purple. And these are gray. I can't scroll up here, a bit down. I'm kind of assuming that, let's see. So this is not our... This is not the same addresses up here. No coloring here for what's changed. I think something changed though. Here we can see red, you know. So the next is the coal. And then we get back. Now we should have to make this clearer, let's hop to the code for the function. So we should have just done the gets here, right? This is the only function that we're calling that's external. So maybe not, maybe not. There's another call. I can start to feel I'm a bit tired. So my kids want to see Lord of the Rings. Whatever, if it's number 2, I think. Or is it number 3? Is it number 2? Maybe we saw 2 parts. My brain just dies from watching those boring long films. Sorry if I scared someone here away with no, it's not that I don't think they're good. It's just that we saw the 3 hours and 45 minutes version of the last one, and there's a lots of long fight scenes and stuff. You know, I train martial arts. It's not that I don't like fighting, but it's so long. But I think the next one is the worst. Right, I think so. We'll see. Yeah, anyway, what happened is that the wizard dude fell into that hole, or whatever you call it, ravine, in the mines there, right? And I know, because I saw them long ago with my hubby. And also the long version. So I know what will happen now. But there was a person that died in it. I'm like, I don't like when the good guys dies. Well, I'll have to watch it, I guess. In a few hours, we'll see. Right. So I really maybe should look more carefully at the code, but that's not what we're after now. I want to see the console stack, you know. So let's hop a few more steps. Seriously, there's something I would like to know here. Will we get some question when there's input to actually input stuff? So when you run it, are you not supposed to get a question about like arguments or things? Not that this program has them. Well, F8, right? Just double checking. So we don't want to go into that call here. So this is the stack. So I should have realized, yeah, but I kind of did. Since we have purple here, I assume this was where the stack pointer is, and I just checked. ESP here is this address, right? So that's where it is. And here we can also see that we had a return here. This is good. Yeah, nice. Though I would like to have it bigger. We can scroll this a bit. And we don't have to see these. So we want to look at the stack a lot. So now, if you look at the rest here, there are several more calls. I didn't read it all. Where are we? I was thinking there's a mess. There's a like arrow, right? A little green arrow. So here we have a red. And cool. We have a print of push -1. So, am I blind or am I scrolling badly? Test. So, I feel like this is bad scrolling. You know, I scroll several times and it doesn't happen. And then suddenly it hops a bit. Scroll, 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 scroll. Now it worked several times. Scroll, scroll. Maybe it's when I scroll quicker. Yeah, I'm kind of thinking of stepping into stuff instead. That might take ages. And we might have to set breakpoints instead. I'm sure you can do it here, right? So maybe I can even click stuff. Alright. Toggle breakpoint F2. So we can like click stuff and do toggle breakpoint on them. Let's see if we can fix that. Sender. So the center vertically and center horizontally. Yeah. Because it could be the other way. I mean, it could be in the horizontal direction or on the horizontal axis, right? So I'm like always, is that right? It was this time. So food message, bye bye. Right. Yeah. So I realized how to set breakpoints. If I click now, I can scroll. Right. So what I'm currently thinking is, how do we get our input into this, right? So let's just continue stepping and see what happens. So we have set a value of EBX plus 4 times 8. He eats so quickly. He's always already running down with the plate. Running quickly. Speed. Everything we do. ESP sub. Yeah, so this hops automatically up and down. Nice. And did I like miss anything? So when it hops, it's not just positive. So it pushed all of those. Then it's XORing there. And then we have the next call. And I'm going to step over this now. Like, I don't think I like
Pedro
that
Freitas
this one
says BS
sprouts.
viewers on mastable.com/66nc.
Yeah.
Fixit 42 bot says message removed.
Yeah, I couldn't really do anything about that, you know. So they're still red even when they're removed. So they are in the current patterns for spam messages. So let's not think too much this time. Let's mostly just step through it. So there we XOR'd EBP with EBP and EBP 0, and this one wasn't marked red. Why? Poppy sigh. So many pushes. So Maybe this one can take this tiny space. And maybe I should make the size bigger, right? You can't see it still, right? I think I have to restart the program though for every font size change. So if we just run the whole thing with F9 then. The debugged application exited normally. So if we, I guess we open again, restart, and we F9, it does stop here. Then it exits. So how would I get input in here? This program is called EDB. What if we attach instead? Let's try the attach one, right? So what we have running on Kali, not Windows. Is actually a debug here, right? So maybe we do it here and see. Maybe it's easier to see things there. Oh, that would be stupid, right? But I know this more now than the other one, which doesn't mean that I should only use this, but means that I need to learn the other one better too. Yeah. Alright, we need to move there. So, well, let's see, where were I? I was going to check. First of all, well, these addresses the same. How do I list this in EDB, right? So here we should just be able to tab. So what if we restart this and then we see if we can find a way to list stuff. Application arguments. So here is the arguments bit, but I can't add anything here. It's just like a view thingy. Yeah, right. I've seen that before. There's no way for me to change it, I think. We can run, restart, detach. Not there. Plugins. Oh. Yeah, so I really want to do a box too. I feel like we're only doing buffer overflow. I'm only doing that. So I'm thinking of splitting the days. So, for example, like 2 days I do this kind of digging thing, and 2 days I do like boxes, and 1 day I do like whatever other random stuff we need to fix, or 2, or I don't know. Just a thought. We'll see. So I just skipped over these, just didn't look at what it was, because it was actually a function finder, and that's what I was looking for. So we have the functions. Or do we? Because this is not the functions. So I wanted something this, like this, right? Here we have a function when. And I didn't remember the code, so I should probably have it up. Yeah, we're supposed to hop to the win. That's why it exists. So it's not actually in there. It's not being called by a function, but we are calling. So if we think calls here now, so this of course is a call for printf, and this one is, and then this one is for this address fp here. So we have 1, 2, 3, 4 calls, and the if. I didn't see the if. Oh my god, no such. I'm thinking how it would end up. This kind of basic. Is it 0? Or just if? Pointer? Yeah, we need to like dig into it more. So we might be okay with this too, because I was really going to start with the next one, and it's just like 1 hour left probably. So digging into something like kind of simple forever might not be a good thing. So I don't think these streams are so popular either. Though, why not stream it, you know? Oh, I shouldn't have that open. Right. Oh, so in this one too, we need to get arguments in there, but here I know how to do it. So permissions. You must select a region. Oh. So that's how it works. So here it is. And these are running, you know, separately. 0804, 84, 24. 0804, 84, 24. To say it better. It's still the same address. So this is running in the debugger here, and it's running in the debugger here, and it's here. So this, let's do this one then, right? No functions found. So this is it. What is graph? So what, you can select several things. So that's one of the few, very, very few things I don't like about this. Yes, I imagine this being great for other things, you know. And also, what does red and green mean? I think I know though. This is the F, right? GE. This is the jump. This is F. And if we don't go into the F, we just leave here. The last few lines here. But if we do, we will call first printf, and we will set stuff off for printf, and then we will call the function. So this is just setting that up. So that's kind of nice, right? Having an image of this. Maybe we should put this in the notes even. So did I restart my computer? No, ShareX is still running. So we can just take a ShareX screenshot here of this. So I don't know if I recommend this program because I have so many things bugging with cutting and pasting, and when I restart this it works, right? So here's the F. So this helped make the code more readable, right? This is an extra section again. Looking at the program in EDB GUI app, right? Main I'm thinking overview of what is this actually called. What was this called? Graph selected function. So we'll graph off then, right? In the notes. Graph of main. So here we can clearly see the if and the calls the if the red line arrow, it's not a line, if it's true, well, yeah, that's true. Going to call print f, and then the function pointers function. Yeah, I should do this, right? The green. So why have a red arrow for true and green for false? Is it just me? The green arrow skips the contents of the if and hops straight to 0x 0.0484 78 77 where we have the leave and red. So what else can we see? So is it just me that thought that they looked much longer here, right? So let's actually see if we can put a... So we can see the addresses here, right? But I also have them on the image. So and we have Win's address here too. Start addresses. So this address here. So it's not the same type of address apparently, right? So inspect instruction. Now we have to just see what this does. So what if we do this on a call? So that was a function finder. Heap analyzer. We'll have to look at this, but the program that actually uses heap, right? So we have an example that does that. Both stack and heap example. So I'm drinking orange juice. I didn't want to go make tea or anything. And my water was still on my bike actually. Didn't carry it all in. Symbol viewer. So this is a symbol list that we can see in the command line ones. I wouldn't say the output is much prettier, right? So is there anything else we could do? Yes, there is. Follow. So printf. This is interesting, right? So here we can see what these means. Come on, phone, allow me to switch. So it complained about not being able to charge, and then it didn't want to control stream anymore. So now there. So here we can see we have 8048 350. So it is the printf one, which we already knew, but still, this makes it easier to see it up here too, right? So if we go up here and we look at these calls, so now we can see what these actually, what this is, right, easier. Yeah, so the win function's call won't be here. So I already know this will be get, but we wanna like learn this here, right? So here it is. So 80483330. There. But this function then, when we can't do the function thing here, right? So let's close and let's go to plugins, function finder, find in this part of it, wrong window. And you can see there are more things, not more than that then. So now we have win. So what if we do the graphical thing here? Of course it's not much. So I guess we will F4 this one too, meaning screenshot that, right? So this might seem like too much repetition, but I think it's nice to look at all the things. This is too big. I'll just do a pipe 700, maybe too big still, right? 600. Well, that's about the size of the previous ones. So now we can compare this printf up here with this printf and see that they have the same address, right? So my biggest problem right now is these addresses. I don't know why they're so different. So what is this really, right? So let's look at main's address. Yeah, and in the calls they cut the 0, leaving 0 off. So that's why it's 1 digit less. So that's all logical, but here, if we were to restart this now, can I like hop there? Like, look, we could. Right, so it actually is this address. Good. I was like, why are we in this place? Yeah, so then my problem is solved. It is the same. So we were probably somewhere else here, and then Oh look, it's here in the memory listing. So, there. Because I was starting to not like that. Yeah, and here we can see the F. And there's a nice arrow for the jump to the leave. So, nice. And there's tiny selections here too. We can see the functions. So where are we? If we F8 here, where are we on this address? So let's F7 stuff instead, right? So now I'm looking at the call addresses here because didn't get, this wasn't like logical to me. But if we don't step into stuff, we will just skip the whole program then. So as long as we are in this other section of memory, we're not really in our program, right? We didn't put a breakpoint at the start of main. That's what we kinda should have done. This is very interesting. So yeah. So I'm looking at all the jump ones, the calls, well, jumps too, I guess, but when will it hop there? So we're in a loop. Yeah, so this is not something I will do a million times, okay? Yeah, let's see if we can make a so to find the function, we go to the function finder, we click here, we click find, we double click main, we hop here, we're going to right click and we're going to see if we can see the toggle breakpoint there, F2. So there's already was a breakpoint there by default then. So then I could just run the program and end up there. So if I F9 now, where is it? Here, it's separate. I looked only these and it's there. So will this one end up being 08048438 when I click F9? Yes, so that is by default start of main as a breakpoint, and this looks so much more logical than I was trying to like merge the code we saw before with assembler code with the C code and it didn't fit. And then I saw the function for this thing for main. I was like, right, this makes sense. Why didn't I see these instructions? Why is this memory address and we had a lot of F's in the address before? It was in the wrong place, right? Good. So now it's all making sense. And we should have the win just above here. So this is where we're supposed to hop with the help of input, and I don't know how to make input in EDB. So let's solve that. Let's solve
Fixit 42 bot says new follower in skim 8R. Less than 3.
So let's Google. Right, so I did start I guess I made a new account on the Academy yesterday. So we'll see if I do that later. So, right, let's actually click here. Because what I saw was not that. That was yesterday's Garbox. I saw there was a buffer overflow where that was a free one. So maybe we'll do this next time, or maybe I'll just... It says 7 hours. That's nice. It's not like just click through it in 2 seconds. That I like. There's also other stuff here, of course. Other interesting... I did the introduction one yesterday. That's the only thing I've done. So, what's most interesting here? I saw 80. Right, so... 80. Hold up. Kerberos attacks. 2 days. There's supposed to be lots of content. No, this isn't. This is tier 3. Yeah, so something happened there. I clicked this one yesterday. I didn't remember. So I was just watching the free ones for now. We always start with the free content, right? So, but I know there was 80 stuff here. So, okay, SQLize. Here's the buffer overflow ones. JavaScript obfuscation, maybe. Here's 80. Yeah, because I think the other one was a pay one, right? Also, this could be nice. Getting started. Yeah, I should probably run through these, but that's not for stream. I guess it will be click, 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 you know. But there might be something in there that's interesting. That's why I'm not doing them. Network traffic analysis, always fun. I like digging in stuff. But mostly I like... And here we have x86 buffer overflow. So there's actually 2 ones. This is 8 hours. What was the other one? And hardware attacks. So I guess I should do macOS, right? So after they switched to using Linux, I think it's not as horrible to hear the word Mac. I don't know. I've never used one. What you don't know, you don't like. Is that it? No, it's things like making apps for Mac stuff. You know, you have to pay and pay and pay and pay and have their hardware. So we have to pay and pay and pay more. Nah. I think, and also locked. You can't use widgets on their phones, right, and stuff. Have they changed it? I don't think so. They want it so secure, so it's not usable. There has to be balance. Vulnerability assessment. Yeah, it's lots of fun stuff. But here we have Linux, so let's just take a quick look. So, I don't know what these icons mean yet. Might this be theory and then loving stuff? Document, document, document. Interactive, yeah. So in this intro thing, they said something about these being interactive. So, it looks like the normal ones, right? So that's the one I had up on the VM. Relevant paths, yeah. Costing a lot of money, I'm assuming, but this is 50. So for free, I got 70 of those. You got, I think you had like 30 from the start. Then you had, when you did the introduction thingy, you got 40, and 10 of them was for answering some question or something, like starting their terminal thingy. like tiny VM. Yes, I don't know yet. I haven't tried it. So this was just like, of course they will be like ads, right? But I guess you could start this somewhere. All right, unlock it here. Yeah, so we can click this. We will use 10 of our free. What are they? Cubes. Spend. It doesn't say. I think it was cubes. And then we can start it and do it. So let's do that another day. And this was just from that start one. It had a link. But let's Google now. So how EDB how I forgot what I was going to search. That's good. Yeah. Arguments. How add argument. So Evans Debugger is the name of it. That's what EDB stands for. We can also look at the GitHub page. Yeah, so this is the GitHub page. This is an issue. And can you please tell me? These start an issue with a question. There are essentially two methods to do this. You can run EDB from the command line using run, for example. You can use UI to set application arguments for the next open program. You can go to some options, application arguments. Oh, this is horrible. Yeah, so the command, starting a GUI application from the command line, and you can't like change them while it's open, even if you use a GUI to do it. Yeah, the first method works well. That's what I would prefer. Option work with, well, would you want to? You would want to try different things, right? And test it quickly, and then you would use the command line so you can do small changes without having to restart the whole thing in a messy way. You can confirm that it's broken and to unintuitive to use it correctly. Do as follows. Run EDB options application arguments plus button. Replace the text with close. File open. Bin sleep. F9 exit. Because it's automatically pausing it to start a main then. We just learned get exit code 1 with third option with just words. So specify arguments in the run dialog. Right, so this is let's see, where is the run dialog? How do I see a run dialog? So what if I kill this? I can't run, I have to restart. There's no run dialog. So when I open something, here I can set arguments. So file open dialog, I would call this. Right. So let's put some Python there. So I want to copy something. Like I'll have to just scroll up. Will this work? So if I start the program from this, the color button, you know, and by the way, I have it down because I have the VM1 here, VMware, and they like overlap all the time. It's the Windows one doesn't pop up when this is selected. So, right. So I've put it here. So when it's a GUI program, it should work without having to start it from the command line. There are exceptions, like RDP. I always start from the command line, though it's a GUI thing. So let's see. Well, can it do Python there? I guess it should, because this will probably just make it into a command line, right? I don't know yet. What if we open this? And now we run it with F9. End up in here, in main. Then we check the stack here. So we have both, we can see both. We don't, that's enough, right? Right, I should change the font size here too. It didn't look good to increase, that's why I didn't. So it's nice in my throat to drink some orange juice. So let's go. So we will now F8 step over stuff. Meaning we won't hop into the gets here. Juice maybe wasn't good for my throat anyway, it was too strong. So we can see the stack, and it hops to the top of the stack here. So it's really not interesting on the stack for this one. Now we will see if our Python one worked. So it should be easier to see there. So we can see the purple here, and if we look at ESP here, it is at 3670. So it's at that place. But I'm thinking, yeah, so I should aim for this drag thingy here. That's where I should drag it up and down. I don't have to try and find it every time. Since we have different height in different places, it's a bit messy. Oh, I just noticed this line here. So now, if we manage to get the stuff into there, this should hop in here, right? I'm actually doing yes. So it didn't. No arguments. So let's do open again, and let's do 1, 2, 3 here. That's more than fits, okay? That's 70 characters. About. Might have skipped one or two, or added some. So we F9, F8. Let's drag this thing up a bit. Yeah, so what I would like here is to have a shell thingy, a command line where you could see the input and output and run the commands from there. That would have been so great. Let's actually stop this. So this one is already running R2, right? Let's quit R2. And let's do EDB, and let's see if we can, yeah. So we don't really want arguments. That's what we want. We want input during the, right. So it was my bad. Because I didn't want to put arguments in there. I want input during the applications. When it's run, add input to program. Yeah, let's just go here and let's check there must be like documentation for it, right? Oh my god, it's bright light. And mine is not then, because I didn't think of that as a bad thing. So I just started now from command line with the one I had open there. It works. It says update available. And it's black. Nice. What if we can just pipe stuff into EDB and it will be piped into the program we start? What do you think? So this is the correct one. So what if we pipe this into EDB this, right? Just for testing. Yeah, I kind of thought so. So let's do run. You're on the wrong screen. I thought so. Good, I have a previews. Yeah, so we're running a program. We don't have any arguments. We just want input to it. So we just run it to here. We stop until after the gets. Yay! Look, we have lots of A's here. We have lots of A's. See? See? So let's continue here. We should get output here. Right, so we're now inside here. So I'm grateful for this. This is the one dude who made this. That's amazing in that case. Whoever did it. So we're definitely not stepping into the printf. So there. I'm like, can I see the output somewhere? Can I, since I started it on the command line? Yes, we can see the output. So this program is not supposed to be run GUI only. We have stuff here, right? We could pipe to it. We get information here. It's not like it's starting the GUI and skipping this, right? And this is the program's information. So we can see that it's using the wrong address here. It's adding the C2 here in it. That's just me probably managing to paste a line again. So I'm liking this more and more. More and more. It's growing on me here. So we have all the A's here. Yeah, I think I found this program from just checking out the menu, right? Well, I guess I checked this one out and went through the list. And there are several command line ones here that we don't want to start that way. Definitely. Now we know that we want to start this one too on the command line. Or we wouldn't get that output. We wouldn't see this. We wouldn't see that it was printing the wrong address. But what we can see is what did it actually print, right? So I guess one of these arguments here is the address. So yeah, I scrolled down. That was me. Here we have C2 4, and what we're putting there to hop back over here is this 248404 248404 248404, and the last one is a 08. So I guess it's up here. So the C2 is squashed in there. And this is what I'm investigating here. This is the reason why we're in there. And why can't I see more there? I'll have to drag this one. Yeah. So zero 0804. It's because the function's address, it's a win function's address. That's, well, here, this address. That's where we want to go. So we want to have that here. But it pops in this C2 in the middle. And we did this on another VM that is also made for doing buffer overflows. But I wanted to see this in the stack like this, what it looked like. But I do feel I can see it better when I would prefer to have a... Can I change? Show address, hex, ASCII, comments. So what if I remove comments? It doesn't show more. It shows less. Right. I guess it's good, okay, to have the comments there. But it's good that we can adjust it. And there's a set font there. There's no set font here when I right click, is there? Oh, I can change the value. So okay. So why did these increase in size? Very logical and nice. I clicked something by mistake, I know that. But I also know that if you go to the preferences here, the options, you can set the font size in appearance, and I have set the different values here. So the register view is 16. So if we set this one to 18 too, and we close, and then we close it, and we run it again. Oh, right. That was my managing to copy a line again. And we still have an update. So now, look, it's kind of buggy. There's definitely a few bugs here, you know? A few bugs. So if I like edit these whatever values, well, let's click whatever, modify. Let's do an 1 here, there, so it's modified, and then we just close this. Let's look at the preferences again. Let's do 20, 18. I don't know how smart it is. Close. It always up to a tiny size. We close it. We open it. And it's kind of like, well, this one is big too now. Yeah. So I can't click the menu. Alright, that's that message again. Right, so I'm going to do a update. EBD update on this one. But not on stream, because it might take some time. So I'm assuming this will be updated. Otherwise we'll do it manually. I love EBD. It's wonderful. So, bye bye Windows update, right? Preferences, appearance. Data view settings, show columns and addresses, show function offsets and hexadecimal. Theme, system. Right, so system, it's taking the dark from system. That's fine. I'm thinking like changes will take effect after start. Maybe we'll also reset stuff. Like if we make this 20 points now, close. close, start. Yeah, so it's flipped out even more. Totally odd here. Let's say change the size here of the side. Right, this one makes me not being able to modify it. Let's just make sure that it has the space to fit the text. Right? So there are bugs. Let's just restart once more. Oh, look. I didn't even have to like do anything. I just went into settings and it's like reset the size. Oh, look, more things went into the right size. So if I don't really want this big, so let's put it back to appearance. Like let's try 18, right? So I had 16 before. This is not 16. Then we start it. We close it. We start it. Changing all the time here. We close it. We start it. Oh well, what do you think? So it would be nice to have a same size of everything. That's like all my goal is right now. Yeah, so I had problems getting the text bigger, but it wasn't this hoppy, right? Wasn't this hopping around all over the place. Yeah. So anyway, we still run the right command. So let's continue. If I do F9, we hop to the main automatic breakpoint. I was going to add one. Notice it was one there already. We can step through the program here. So I'm just reading here. 48438, that's main. Why is that here? So everything should be prepared here for. So what really happened? Yeah, so this still gets the coloring. So EAX has there the return value of the call. Which is all the A's. And we can see that all the A's are also here, including this. And here we can see that the 08 is here. And there's a C2 inserted in the middle. That was not there when we sent it, because we sent this. So it pushes it over to this one. Yeah, I want to do it with one X-ray and see how it looks then. So let's just do the same but with 65 A's. So I'm just exploring what my modern computer is doing with this program without security, right? So we do F9 to hop to the breakpoint at the start of main. Then we F8 to step over the things. And the important line is here with where it actually gets the arguments. The call forgets. Then we have all the A's. And now we put an extra A here. So we can see the extra A being here. In the place, this is where our pointer is really, right? So now it pushed this one out. So we have the 4 there too. So these two were pushed to the next one. And before only this one was pushed there. So it is all logical and working as I guess it should. So I'm curious why there's a C2 here. I mean, what is it in my computer that makes the stack safe? So the first thing to test now is to actually compile it myself, right? So I guess I can Control C this here and it will like close the thing, right? So it closed, I couldn't tab to it. So let's nano, that's the one with stack and heap. So stack3.c, because it's not here already. It's not compiled on this machine. Just looking for my notes. And we're going up to the code that we found by Googling, because the page where these are seem to be like bye-bye. Old, it's not new stuff. So we paste this here, we SX it. Then I have actually the compile command here, right? So we don't have to think or do anything. It's in the notes because I compiled it on the other machine when we tested it here. So here, this should be the same compile, right? Should be the same, but let's look at it. We don't overwrite this, so this one we will call stack3 local compile. Well, local is okay, right? Compiled. Right, so I want to compare them. We will get the warnings about the gets is not safe, which is very obvious, right? So now we can see the difference between their stack3 and ours, that they're not the same at all. And this is also from 2011. So it's not new, as I said. And that website is not there. And it's not odd that it's not there. But we still play with these, right? So let's now run the new one instead here. So we do now stack compiled and see how this will behave, if it will be the same way or if it will be different. It should be the same code. Let's do F9 and see where we end up. So we're in a different place here, meaning our argument would not work, of course. We could just check anyway on, right, also we didn't set it to compile as 32-bit. I need to learn to do that. So let's stop this and remake the compilation because I want it to be still 32-bit. So let's see, we want GCC compile 32-bit. So M32. In order to compile with 32-bit GCC, add the flag M32 You will get an error. Okay. We'll see. So lots of stuff is already installed. So, oh my god. I clicked space and scroll down on the web page. So space M32 fatal error, no such file. Yeah, so that's another error message. So let's do what they suggest. Just changing it a bit. Yeah, so it added the B itself. I tabbed. So this should work. If it fixes the problem, we don't know yet. So let's see. So I didn't say it only to update that, but I don't think it's very much anyway. Yeah, right. Yeah. I didn't do an update, so it's safe. So let's try it again. We get the warning. But TMP function main, yeah, that's what gets. So the tool gets warnings. Let's check the files and see. It is 1706. So I'm sure it was a minute since before we started looking. So it's supposed to be new compile here. So we will see when we open it. Like this, if it is a 32-bit now. Yeah, good. But this is kind of funny, right? The sizes, oh, you can't see. So the sizes here are going crazy. What? Alright, right. There. Now you can see the sizes here are going crazy. It's like hopping around. So I tried to set the font size to this size, and it's like sometimes working, just sometimes. It's buggy. It's not the whole world. Well, I could be it down here, right? So we press F9 to hop to the automatic breakpoint at the start of main that we noticed. I thought at least. Maybe it's not an automatic breakpoint here. Yeah. So it's just a new name for it. So yeah, and we can see here also it has the new name here. So if we F8 through this now, actually let's also check the function finder, and let's see if we can find it here. So here we have win, stack3 compiled win. So I guess I will put this somewhere. So I know I'm not taking notes as I usually do. I'm just playing, so plain. So new compiled. narration. Functions. Let's actually make this nicely sized, and let's do a screenshot of this. So there. Well, I guess it can be like this, right? Like this. Yeah, we'll cut this out. We'll cut this out anyway. It doesn't matter. So let's get this window. Maybe should have cut tighter. Yeah, it's not pretty, is it? Whatever. I can edit the image if I really want it. So we have 0x, 08, 04, 91, 86. There. So we will just quickly restart it with updated numbers, so that it actually is the correct one. So 08, 04 was the same, but then we have 91 instead of 84, and we have 86 there. So now we're running it with the correct, not argument, but input. And oh, yeah, you see now, right? Only one is the wrong size now. Well, 2, EIP 2. This one's not important. Yeah, so F9 to hop to the start of main, and let's stop over the lines here. So here is the line where we get stuff. So no. There it is. So what was I doing? What is this then? Yeah, so it's recompiled it differently. So I don't know what this call is. Get PC something. Anyway, also we can see here that this is all the things, and this is kind of the interesting bit down here. So we can see the values 08, 04, 91, and 86. Oh, then we have a C2 in 86. So the C2 has inserted itself in the same place in what we inputted. I just forgot to remove the extra character, right? So it's still doing 65 characters. So if we hop back to 64, this is quick, so we can do it. And we F9 this, and we go down to not this call then, but the next call. There is the gets call, gets the input, which is lying there waiting for it. And I guess we actually could have hopped over here and given it something maybe, but it wouldn't have waited, right? It wouldn't have been waiting. I'm curious to know how it works there. So anyway, now we had it waiting. So now we can scroll down, we can compare here. So sorry for clicking it, I don't want to select that, whatever. Here we have let's see, after the A's, we have the C2 is here. But we also have a C2 here now. So we have two C2s. So I'm curious to Google C2, right? So we're supposed to have 08049186, but now we have two C2s in there. Yeah. So, C2 inserted into my string y. C2 was not a good thing, right? C2, let's do that, because that's... So what is C2, by the way? We'll probably find out, right? This is a totally different thing. I'm curious. Let's just CyberChef C2. I wouldn't know now. I don't know what C2 is. So C2 from hex. Okay. So nothing special, right? I don't know. This doesn't speak ASCII. Let's do this one instead. Let's look at the ASCII table here. Let's C2. So this is not, this is too high. It's too high, right? It ends at 7. Extended. Here we go. No, that doesn't help. What? So I just wanted to do 128, 129, and we get 8,220. So let's just get a 8-bit ASCII, please. So recently, if I install some kind of game on my mobile phone, I get this thing. That's annoying. Couldn't there be a no, you know? I want people just to click, I guess. Not that I really care, but I guess this is a nice URL. So now let's see. Here, 128. So ABC C2. Yeah, so we get this character here too. And this is what it got. So just wanted to double check. So, what do we do with this information? It's more like we can get a better question to ChatGPT, right? So, so it's not like I have secret stuff here. Linux,
Avesh029 says hello.
Hi, how are you? Welcome in. So, right. Yes, I was thinking we probably have something similar from ChatGPT, but I don't think it's worth trying to find it.
Avesh029 says all good. Avesh029 says and you.
Yeah, I'm great. And it's Friday night soon. But I'll have to watch Lord of the Rings long one with my kids, so we'll see. This is more fun. Right, so I'm kind of thinking...
Avesh029 says that's great, D.
I'm thinking like if it was a random character, I wouldn't be as curious, but now I'm more curious. It's a function pointer on this one. A function pointer. On a older VM. On a modern VM. With Kali Linux. On an older VM. 32 bits. And here we'll just... No, let's add it later. Normaler it works. But it was actually added an extra byte for C code. Not that it matters, but it sometimes it can like do examples, right? And we could also give it like the compiled with so I got my wrong, oh gosh, wrong terminal. It's this one. Right, I know I'm down in the corner there. It's so we can see the register's values in EDB. So I'm just currently looking for the compile command I used. And it might suggest us to do other things. I know that I saw somewhere a I saw something else. to do something on the machine too, to do these things, to turn off stuff, right? So running with compiled with, running with, and then I'm going to go back here and get the command when we run it. So let's copy that, paste. I'm just adding to the data, and as the last thing, let's see if we can copy from this program, right? I don't think we can. Copy to clipboard, copy address. I want both, of course. Seriously. So this will end up in Notepad here first. So no Notepad. There. Yeah, so we got the addresses too. Alright, so we can see how this was split up by two C2s in the memory. So stack looks like there. What do you think it will say? The issue you're encountering with the insertion of C2 into the function pointer can be attributed to the feature of modern processors and operating systems known as pointer authentication or memory protection mechanisms. Yes. Specifically, this program is likely related to a combination of an address space layout randomization and non-executable NX stack or data execution prevention DP, and also possibly pointer authentication codes pack on certain ARM architecture. This is not ARM. I should have said x86. Here's a breakdown of the likely causes why the older VM behaves differently. Yeah. Even though you disable stack protection, modern systems still often have other protections like stack canaries. So this is with the file, you know, it could be an old program, not safe, but you still want it to be safe on your computer. So this is why we're looking into this. Modern systems still often have other protections like stack canaries, which have special values placed on the stack to detect buffer overflows. These might not be present on all the system or might be disabled. Yeah, so that's why we used a special machine that's supposed to do this when we couldn't do the original one. Address space layout randomization. ASLR randomizes the memory address used by system and user programs, which makes it harder to predict where your injected code or specific addresses will reside. Well, if ASLR is enabled, your injected address might not be valid. This could explain why the behavior is inconsistent between your two environments. Non-executable stack TP. Modern systems enforce a non-executable stack policy, meaning that even if you can successfully override a pointer, the stack memory cannot be executed. This can lead to various issues, including the behavior you're seeing with the injected address gets altered. But it's not like it's altered, it's like stuff put in between. So I guess it's altered, but it's not like it's overridden or anything, you know? So it's funny. It actually overwrites more of the memory that you shouldn't touch. Really, right? So, it should be saying, if it was really good, it would be saying, Error! You can't overwrite this memory because it's outside of where you're allowed to edit the memory of the stack, right? That's kind of what I would have wanted to say. I don't know. So, pointer authentication and pack on ARM. Yeah, so we can skip this, but we can read it anyway. Pointer authentication involves adding cryptographic. I'll skip it because I don't want to mess up my memory of things there. Yeah, so like some modern security features like these. If ASLR is disabled, the address you overwrite into FP will be consistent and well valid. Allowed the overflow to work as intended. Allowing the NX, if NX is not enforced, the stack is executable, so exploit can proceed. Potential solutions: disabling ASLR. You can disable ASLR. It should kind of not say exploit since it's a function. We're just trying to practice calling a function, but it's probably copying text from somewhere. You can disable ASLR temporarily by running the following command. Yeah. This is not how I would change stuff. But I guess this is a Boolean value then. This disables ASLR, making memory addresses more predictable. Ensure NX is disabled. Make sure the stack is executable. Some VMs or compilers might enforce NX. In some cases, you can disable it via compilation flags or VM configuration, but this is less straightforward. Use a ret to libc attack. Instead of directly executing code on the stack, you might need to use a more sophisticated technique like a return to libc, which bypasses the need to execute code on the stack. Okay, cool, getting tips there. Testing in a controlled environment. Continue testing in your older VM if it's important to see the basic buffer overflow without modern mitigations. Simulating older architectures. If it's possible and if the purpose is education, consider using an emulator for an older architecture to set up a VM that mimics older, less secure environments. Yeah, so I just wanted details on these. We got a few details. We got a tiny hint to check this thing. Ret to libc attack. But what I really wanted was to know exactly also why it's C2. So let's actually know this. Is there a reason it's C2? I got one C2 added before I recompiled using the original L file, not one I compiled. So we got a different result. But still the same. Jar inserted. Was there something else? So I'm starting to think of things like pizza and watching Friday night movie with my family. But my hubby's not home yet, so I think we'll go on until at least until he calls. He usually calls when he's going back home. So the insertion of C2 byte in Overflow scenario is likely related to how modern systems handle utilization memory and pointer integrity checks. There's a more detailed explanation. Pointer authentication, which might explain. Yeah, so it's like repeating itself. So I'm asking about the specific value. Yeah, why C2 specifically? Is often associated with the first byte in a multi-byte sequence in UTF-8 encoding for characters in the range. Yeah, so when we read the other thing, I was thinking, is this some kind of conversion thingy too, right? For characters like U plus, U plus. However, in the context of Overflow, is likely coincidental. Memory initialization of system or compiler, or specific sequence of how the runtime handles clears memory, an artifact of how function pointers are checked and aligned on your specific setup. So what I want to do really is to check the memory of the TryHackMe virtual machine and see what it added between there. Well, that one, if it was just like random space, because we had to do 32 instead of 64, 72, and 72 decimal instead of 64 decimal. So yeah, I want to know. So someone might say we didn't do anything today because we didn't do a new like task, right, or a new exercise, but we dug into this one, right? Let's see. Let's start checking out this actually, because I won't start with the stack 4 now, and I don't want to spend the rest of stream making notes. That would be boring. So let's actually yeah, I'm going to finish that one in the weekend. Because I can't stream, it's not allowed. It's not allowed to stream. So we'll see if we need anything. I have the normal VPN. I don't know if the Academy uses the same, if it ever needs one. But here we have a my throat is starting to go a bit rough, so I'm actually going to select this and let's let the TTS read. Oh well, I can read this first. So, overflows are common overflows, common vulnerabilities in software application that can be exploited to achieve remote code execution (RCE) or perform a denial of service attack. These vulnerabilities are caused by insecure coding, resulting in an attacker being able to overrun the program's buffer and overwrite adjacent memory locations, changing the program's execution path and resulting in unintended actions. So, TTSing the rest.
Module summary. This module introduces buffer overflow attacks, principles such as CPU architecture and CPU registers, and walks through the basics of exploit development and shellcode generation. We will also walk through a public exploit proof of concept and cover techniques for preventing these types of attacks. In this module, we will cover an introduction to buffer overflows, the basics of exploit development, dealing with shellcode length and bad characters, public exploit modification, buffer overflow prevention, CREST CPSA/CRT related sections, all sections, CREST CCTINF related sections,
What's that?
all sections. This module is broken down into sections with accompanying hands-on exercises to practice each of the tactics and techniques we cover. The module ends with a practical hands-on skills assessment to gauge your understanding of the various topic areas. As you work through the module, you will see example commands and command output for the various topics introduced. It is worth reproducing as many of these examples as possible to reinforce further the concepts introduced in each section. You can do this in the punbox provided in the interactive sections or your own virtual machine.
Yeah,
you can start and stop the module at any time and pick up where you left off.
Just general
There is no time limit or grading, but you must
So-
complete all of the exercises and the skills assessment to receive the maximum number of cubes and have this module marked as complete in any paths you have chosen. The module is classified as medium but assumes a working knowledge of the Linux command line and an
So-
understanding of information security fundamentals.
Where
A firm grasp of the
Okay, so
following
this one
modules can be
requires
considered prerequisites for
107.
successful completion of this
and these
module.
others are
Introduction to
thousands.
networking.
6,000,
Linux fundamentals.
11,510. So I haven't really, I don't know how their system works, since I'm new. My badges. So it's just like, you did the introduction, right? So I did that last night. But I had to account. I did the introduction long ago. First weekly streak. How can I get a streak from doing something once? Odd. So I just connected my normal HTTP account. I created one like a few weeks ago that I didn't look at, with one of my other emails, and it seemed like it couldn't really handle it, you know. So when I logged in, you get this login here, and you have the different ones, and I did this one, and when I clicked here, then I got the question, do you want to use your other account? I'm like, well, okay, yeah, let's do it, right? So there's the modules. We don't want a lot of tabs. So this is the one. Let's go back and let's click that button. But we don't really click it. So this should say start. So, and this is the one, the browser tab where I did click it. So it was funny. So, by the way, let's take the opportunity. So we have 60 here now from the 73 ones. So what happens if I click here? Will it say, you have to pay this much or something, right? So, what? So maybe I can do them all separately, and that's how it works. Intro to Python. So I don't think we need that one anyway. But assembly sounds interesting, right? So what if we click this one? I'm sorry for hopping around. So this is tier 2, meaning it's a paid
Aching
one.
underscore chest underscore blurry underscore site says you are old, tired, and ugly.
Sounds like your name. So, let's see here. Yeah, so apparently, so now I can unenroll there. I don't really get it, how it works. I was expecting to get a, like, you don't have this many cubes, you can't do this, right? Yeah, so favorite list. This is the only one I've done. Introduction. So apparently I can enroll in something and don't do anything there. So let's just start this one now. Buffer overflows overview. So there's a bit of text here. I guess this is the facts one, right? So I will TTS it because my throat is starting to go weekend. It's also already taken it's Friday night here. So let's TTS this.
Buffer overflows have become less common in today's world as modern compilers have built-in memory protections that make it difficult for memory corruption bugs to occur accidentally. That being said, languages like C are not going to go away anytime soon, and they are predominant in embedded software and IoT, Internet of Things. One of my favorite somewhat recent buffer overflows was CVE 2020-13156, which was a heap-based buffer overflow in pseudo. These attacks aren't limited to binaries. A large number of buffer overflows occur in web applications, especially embedded devices which utilize custom web servers. A good example is CVE 2017-12542 with HP ILO, integrated lights out, management devices. Just sending 29 characters in an HTTP header parameter caused a buffer overflow which bypassed login. I like this example because there is no need for an actual payload that you'll read more about later, since the system failed open upon reaching an error. In short, buffer overflows are caused by incorrect program code, which cannot process too large amounts of data correctly by the CPU and can, therefore, manipulate the CPU's processing. Suppose too much data is written to a reserved memory buffer or stack that is not limited, for example. In that case, specific registers will be overwritten, which may allow code to be executed. A buffer overflow can cause the program to crash, corrupt data, or harm data structures in the program's runtime. The last of these can overwrite the specific program's return address with arbitrary data, allowing an attacker to execute commands with the privileges of the process vulnerable to the buffer overflow by passing arbitrary machine code. This code is usually intended to give us more convenient access to the system to use it for our own purposes. Such buffer overflows in common servers and internet worms also exploit client software. A particularly popular target on Unix systems is root access, which gives us all permissions to access the system. However, as is often misunderstood, this does not mean that a buffer overflow that only leads to the privileges of a standard user is harmless. Getting the coveted root access is often much easier if you already have user privileges. Buffer overflows, in addition to programming carelessness, are mainly made possible by computer systems based on the von Neumann architecture. The most significant cause of buffer overflows is the use of programming languages that do not automatically monitor limits of memory buffer or stack to prevent stack-based buffer overflow. These include the C and C++ languages, which emphasize performance and do not require monitoring. For this reason, developers are forced to define such areas in the programming code themselves, which increases vulnerability many times over. These areas are often left undefined for testing purposes or due to carelessness. Even if they were used for testing purposes, they might have been overlooked at the end of the development process. However, not every application environment will likely exhibit a buffer overflow condition. For example, a standalone Java application is least likely compared to others because of how Java handles memory management. Java uses a garbage collection technique to manage memory, which helps prevent buffer overflow conditions.
Yeah. So also this, since I started this yesterday, I think I got like 140 minutes or something. So I guess you should just start this. I hate this kind of limitations. It's better that you see, oh, I like this from the free ones and then pay for it. That's what I did with Trackme. Yeah. But that was a year ago, I think now. Almost. So, exploit development interaction. So, I guess we'll TTS it all again. So, as this is not like...
Exploit development introduction.
Let's hope it's
Exploit development comes in the exploitation phase after specific software and even its versions have been identified. The exploitation phase goal is to use the information found and its analysis to exploit the potential ways to gain interaction and or access to the target system. Developing our own exploits can be very complex and requires a deep understanding of CPU operations and the software's functions that serve as our target. Many exploits are written in different programming languages. One of the most popular programming languages for this is Python because it is easy to understand and easy to write with. In this module, we will focus on basic techniques for exploit development, as a fundamental understanding must be developed before we can deal with the various security mechanisms of memory. Before we run any exploits, we need to understand what an exploit is. An exploit is a code that causes the service to perform an operation we want by abusing the found vulnerability. Such codes often serve as proof of concept, POC, in our reports. There are two types of exploits. One is unknown, zero-day exploits, and the other is known, n-day exploits. Zero-day exploits. An zero-day exploit is a code that exploits a newly identified vulnerability in a specific application. The vulnerability does not need to be public in the application. The danger with such exploits is that if the developers of this application are not informed about the vulnerability, they will likely persist with new updates. NDA exploits. If the vulnerability is published and informs the developers, they will still need time to write a fix to prevent them as soon as possible. When they are published, they talk about NDA exploits, counting the days between the publication of the exploit and an attack on the unpatched systems. Also, these exploits can be divided into 4 different categories: local, remote, DOS, web app. Local exploits. Local exploits/privilege escalation exploits can be executed when opening a file. However, the prerequisite for this is that the local software contains a security vulnerability. Often a local exploit, example in a PDF document or as a macro in a Word or Excel file, first tries to exploit security holes in the program with which the file was imported to achieve a higher privilege level and thus load and execute malicious code/shell code in the operating system. The actual action that the exploit performs is called payload. Remote exploits. The remote exploits very often exploit the buffer overflow vulnerability to get the payload running on the system. This type of exploits differs from local exploits because they can be executed over the network to perform the desired operation. DOS exploits. DOS, denial of service, exploits are codes that prevent other systems from functioning, i.e., cause a crash of individual software or the entire system. Web app exploits. A web application exploit uses a vulnerability in such software. Such vulnerabilities can, for example, allow a command injection on the application itself or the underlying database.
So I will recheck some of that, because I thought, why not multitask when it's not very most stuff, right? But I don't think I think I actually missed something. Let's just get the compile command. So we already have the warning in here, but let's do it anyway. So there we have our compile. We run it with this, so we know that we're using EDB here. We also get the command. This is the overview compared to the much smaller one that we had on our previous compile. So it's also interesting to see how different the code is. I mean, we should get the same result. This is just so many more instructions, right? So we'll have to compare them later, right? Let's focus. I'll see if there's anything else I want from my notes first. Because it would be nice to finish these, so I can close this. Here. So I said I wouldn't do the notes on stream, but it doesn't feel like it's like infinite. We can also see here when I did the listing, it's actually analyzing and telling us, giving us this information here too. You can see it's adding this to the list, so it's not just doing it. Right, so I closed the previous one down to get a screenshot there. Then it didn't take that screenshot anyway. I think that's good enough. We started with making screenshots for the old stuff. I just had to install something here, because 32-bit. That's why. So we're just trying the same thing a lot of times to play with it in EDB, right? So we've started. We should make a note for EDB too, of course, right? Yeah. So this is when I realized I started R2, then I realized, so we're actually on the Kali machine. We don't have to do this. Let's explore EDB instead of R2 and GDB, right? So we have a GUI tool. Let's try it out. And this is yesterday. And I'm sure I have notes for this, but let's make sure. So I'm sure, let's make sure this sounds good, right? So let's see here. What do we need? Nodes. We have lots of nodes. Yeah. So it's finished. So we can close this tab, and then I do exit so I don't close the wrong one. Alright, we need to close it first. There. And this one is where we... this is when we uploaded it to... Right, and this output, I'm very sure I put in there. But let's make sure again. So... I'm not very sure really. Yeah, here it is. So this is where we like got the flag, right? Code flows are successfully changed. But we had to add 72 instead of 64, and I tested a few things to get there. So I'd like to see the stack here too. I'm curious what was added here. It's 8 bytes extra. 8 characters extra. So, what was added? What was in there in the memory in between? And we could see that in R2, but I won't do that now. We don't have that anyway up here, so we can just close this one. So let's exit this too. Alright, that was me overwriting stuff by mistake. Like I pasting, rather dragging it. I don't know how it happens. So that's the last tab, and I don't want you to see the alt stuff because, right. So it was just a desktop. But since I've been doing one of those boxes, then you're not supposed to stream. I want to be like good girl, and not get Hexabugs mad at me. Right. So let's just quickly recheck here. So POC. So what did it say about ND? If the vulnerability is published and informs the developers, they still need time to write. Fix published. Talk about ND. Counting the days between the publication of the exploit and the attack on an unpatched system. Doesn't totally explain it, I think. Well, so I've heard the word. Whatever, I get kind of what it is. That's, I guess, what they're after, right? So, local exploits. Exploit can be executed when opening a file. However, for this is that the local software contains a security vulnerability. The actual action to perform that exploit performs called payload. Remote exploits. Very often, this type of exploit is from local exploits because it can be executed over the network and perform the desired operation. DOS. We know what DOS is, right? A web application exploit uses the vulnerability in such software, such as vulnerabilities can, for example, allow a command injection and action. Well. I guess it's better than I read myself, right? Even if my throat will I won't have to talk during that movie later. CPU architecture. The architecture of the von Neumann was developed by Hungarian mathematician John von Neumann, and it consists of 4 functional units: memory, control unit, ALU, input-output. The von Neumann architecture, the most important units are arithmetical, logical unit, control unit, central processing unit, CPU, is responsible for executing the instructions and for flow control. The instructions are executed one after another, step by step. The commands and data are fetched from memory by the CU, that is the control unit. The connection between processor memory and I/O unit is called a bus system, which is not mentioned in the original von Neumann architecture, but plays an essential role in practice. So, bus system, yeah, of course. They need to communicate. All instructions and data are transferred via the bus system. So, I can't click the image in TryHackMe. It will pop up in big. So here I guess I would have to do this, which is a down. It's not as good. And it's also kind of wide, right? We could zoom though. Tiny bit, can't zoom more. So here we have the ALU, the control unit, CU, memory. So memory talks to control unit talks to the ALU. And that also talks to output and input, I/O, and the bus. It's not really there. It's like a shadow behind it all. Well, there's I7 on the image. And they stole my keyboard. And my screens. Kinda. So, memory. There is primary and secondary memory. Primary memory. Cache, RAM, normal memory that is. If we think about it logically, memory is nothing more than a place to store information. We can think of it as leaving something at one of our friends to pick it up again later. But for this, it's necessary to know the friend's address to pick up what we left behind. It is the same as RAM. RAM describes a memory type whose memory allocation can be accessed directly and randomly by their memory address. The cache is integrated. The cache is integrated into the processor and serves as a buffer, which is the best case, ensures the processor is always fed with data and program code. Before the program code and data enter the processor for processing, the RAM serves as data storage. The size of the RAM determines the amount of data that can be stored for the processor. However, the primary memory loses power, all stored contents is lost. Secondary memory is external data storage such as HDD, SSD, flash drives, CD drives, CD. How many people use CD and DVD to save data from your computer now? Which is not directly accessed by CPU, but via other, I/O interfaces. In other words, it is a mass storage device. It's used to permanently store data that does not need to be processed at the moment. Compared to primary memory, it has a higher storage capacity and can store data permanently without power, but much slower. Control unit is responsible for the correct interworking of the processor's individual parts. The internal bus connection is used for the tasks of the CU. The tasks of the CU can be summarized as followed: reading data from the RAM, saving data in RAM, provide, decode, and execute an instruction, processing the inputs from peripheral devices, processing the outputs to peripheral devices, interrupt control, monitoring the entire system. So very specific on all specifics here. The CU contains instruction register IR, which contains all instructions that the processor decodes and executes accordingly. The instruction decoder translates the instruction and passes them to the execution unit, which then executes the instruction. The execution unit transfers the data to the ALU for calculation and receives the result back from there. The data used during execution is temporarily stored in registers. Central processing unit. The CPU is a functional unit in the computer that provides the actual processing power. It is responsible for processing information and controlling the processing operations. To do this, the CPU fetches commands from memory, one after the other, and initiates data processing. The processor is also referred to as a microprocessor when placed in a single electronic unit, such as PCs. Each CPU has an architecture on which it is built. The best known CPU architectures are x86 i3386, AMD and Intel, x86 64, AMD 64, Microsoft and Sun, ARM, Acorn. Each of these CPU architectures is built in a special way called Instruction Set Architecture, ISA, which the CPU uses to execute its processes. ISA therefore describes the behavior of the processor concerning the instruction set used. The instruction sets, I'm thinking about my big Amiga manuals right now. Or their actual hobbies. Well, we put one together too, I think. He was the one who converted me. Though I didn't totally convert from PC to Amiga, but well. That's what we used for a bit. The instruction said we were coding in Mesa New Year's. That's so bad. But we were not in Sweden. We were in Ireland, and we didn't know a lot of people there, so that's why probably. The instruction sets are defined so that they are independent of a specific implementation. We had just moved there, so. Above all, ISA gives us the possibility to understand the unified behavior of machine code and assembly language concerning register, data types, etc. Yeah, there are 4 different types of ISA. CISC, RISC. Yeah, let's read it all. CISC. Complex instruction set computing. RISC, reduced instruction set computing. VLIV, very long instruction word. EPIC, I haven't heard about this one. With the parallel instruction computing. Yeah, so these are the common ones, right? I'm curious to read about the other ones. RISC stands for Reduced Instruction Set Computer. Oh god. Add stuff. Mess. RISC stands for a design of microprocessor architecture aimed to simplify the complexity of the instruction set for assembly programming to one clock cycle. It leads to higher clock frequencies of the CPU, but enables a faster execution because smaller instruction sets are used. By an instruction set, we mean a set of machine instructions that a given processor can execute. We can find RISC in most smartphones today, for example. Nevertheless, pretty much all CPUs have a portion of RISC in them. RISC architectures have a fixed length of instruction defined as 32-bit and 64-bit. CISC. Complex instruction set computer is a processor architecture with an extensive and complex instruction set. Due to historical development of computers and their memory, recurrent sequences of instructions were combined into complicated instructions in second-generation computers. The addressing of CISC architecture does not require 32-bit or 64-bit in contrast to RISC, but it can be done with 8-bit mode. Yeah, so I kind of stopped listening to myself, so I'll just reread it. I was like... I was starting to think, I'm wondering if my hobby will call soon and I'll have to stop. Duties start the addressing answer search. It does not require 32 story counter storage, but can be done with 38-bit mode. Instruction cycle. So they didn't do the other ones. The ones I was curious about, they skipped them. Well. Just mentioning stuff to make people curious here, and then they don't say anything more. Instruction cycle. The instruction set describes a total of machine instructions of a processor. The scope of the instruction set varies considerably depending on processor type. Each CPU may have different instruction cycles and instruction set, but they are all similar in structure, which we can summarize as follows. Fetch. The machine instruction address is read from the instruction address register IAR, which is then loaded from the cache or RAM into the instruction register IR. Decode. The instruction decoder converts the instruction and starts necessary circuits to execute the instruction. This is interesting. Fetch operands. If further data have to be loaded for execution, these are loaded from the cache or RAM into the working registers. But I want to know more details. Executes. The instruction is executed. This can be, for example, operations in the ALU, a jump in the program, the writing back of results into working registers, or the control of peripheral devices. Depending on the result of some instruction, the status register is set, which can be evaluated by subsequent instructions. Update instruction pointer. If no jump execution has been executed in the execute phase, the IAR is now increased by the length of the instruction, so that it points to the next machine instruction. And this we have seen very closely as we have stepped through the assembler and the machine code, right? So now we get into the stuff. So my throat is still sore. And I'm kind of thinking, what has my hobby not called? Let's see. So I'm going to have to call my mom also and order food for her before we watch that video movie. Lord of the Rings later. So no message either. Still working at 18 on a Friday night. I have to call. I'll just there. So I'm just going to go check with my kid what he wants, and we'll probably order now because he will be home in like 25 minutes, and they are a little bit slow.
VR_Mechatronics says, hey, how is going? Hi viewers.
Hi VR, just when I'm leaving, right? Yeah, so we've been playing around with finding data and stuff there, and looking at graphs of functions. This is an F here in the C code, and this is when it's true and false and stuff, and playing with EDB too. Lots of stuff, fun stuff. You'll have to take me soon what you're doing. I have to go check first. Linus, vad skulle du vilja äta idag? Vad vill du ha för mat? Snackgubben, Linus, vad vill du ha för mat? Jag förstår det, men vi ska ju köpa någon sån här thaimat eller pizza. Men då kan vi köpa pizza så kan du äta typ en tredjedel och ha kvar resten till imorgon. Okej. Jag kommer Labban, 2 sekunder. Yes, love. Yes, yes. Make it like. Yes. Yeah, so it'll be pizza today. I'm going to order pizza. So let's see here. So my throat is really a bit bad now, so maybe I shouldn't read so much more. And I know I kind of read the boring part, right? And now the fun stuff begins. And this is like the image. This is the image. I mean, this is what I like. I don't like when it's up and down. This is much better. Also, it doesn't take as much space on the page. So we'll have to read all of this. But maybe I will do it actually when you're not here. So we'll see. So when did we order pizza last? The 9th. So it wasn't that long ago. 2 weeks. Right, that's logical. We ordered Thai, and then we ordered pizza, and then we ordered Thai Friday night food. So you still here? We are. I'll just make a call and order the pizza, because it's usually takes some time. Sometimes they're quick though. Hej, jag skulle vilja beställa. Ska vi se, en kebabpizza. Och en kebabpizza utan grönsaker. Och en pizza med bara ananas på. Och han vill gärna ha mycket ananas, så att man får ofta att det är bara som om det hade varit typ skinka på också och sådär. Men nu är det ju liksom som att alla grejerna på är ersatta med ananas, om man säger. Så gärna mycket på. Tack. Och också en kebabrulle. Utan lök och utan pepperoni. Vad säger jag? Inte utan lök, utan tomat. Och utan pepperoni. Och med extra lök och sallad. Yes. Ja, det är bra så tack. Och hemkörning. Holmbodavägen 95. Och pizzabröd också gärna tack. Tack så mycket. Ja, hej. There, done. Så jag hör vi talking a bit of Swedish. So I guess I'll continue reading for a bit more. Since all my family will be eating pizza today, which is like, as my 16-year-old said, it's a year since I ate that. He likes, like, you know, bought frozen pizza, kind of okay, but not the pizzeria pizza. So we'll see. It's only ananas on his pizza. That's the only thing. So I was saying, like, have a lot on, not just 3 pieces of it. Yeah, pineapple is called in English. I was like, Englification of the Swedish word. It's called ananas. So pineapple is called ananas. It's a funny word. So he has only pineapple on his pizza. So let's read this now. But let's hop my face over there, right? So stack-based buffer overflow. Memory exceptions are the... Okay, before I start, I guess I need to switch ears because I've been going for 4 hours. Oh, that was a long battery. Alright, I was biking first. That's why. So I didn't have this. That's why. 5:46? How did that happen? It feels like it was like 2 hours, maybe? Having fun. I'm having fun. So, stack-based buffer overflow. Let's see if I can turn my shirt a bit there. Memory exceptions are the operating system's reaction to an error in existing software or during the execution of these. This is responsible for most of the security vulnerabilities in program flows in the last decade. Programming errors often occur, leading to buffer overflows used in intention when programming with low abstract languages such as C or C++. Or assembler, right? Nah, you would have controlled that, wouldn't you? These languages are compiled almost directly to machine code. And in contrast to high abstracted languages such as Java or Python, run through little or no control structure operating system. little or no control structure operating system. Well, I wouldn't have written that. Buffer overflows are errors that allow data that is too large to fit in a buffer of the operating system's memory that is not large enough, thereby overflowing this buffer. Yeah, we've been doing this, right? So everybody knows what it is who's been listening to like over a week on this stream. As a result of this mishandling, the memory or the functions of the executed program is overwritten, potentially creating a security vulnerability. Such a program binary file is a general executable file stored on a data storage medium. There are several different file formats for such executable binary files. For example, portable executable format PE is used on Microsoft platforms. Another format for executable files is executable and linking format ELF, supported on all modern Unix variants. If the linker loads such an executable binary file, the program will be executed. The corresponding program code will be loaded into main memory and then executed by the CPU. Program storage data and instruction in memory during initialization and execution. These are data that are displayed in the executed software or entered by the users. Especially for expected user input, a buffer must be created beforehand by saving the input. The instructions are used to model the program flow. Among other things, return addresses stored in the memory. Therefore, where did I get that from? Which refers to other memory addresses and thus defines the program's control flow. If such return addresses are deliberately overridden by using a buffer overflow, an attacker can manipulate program flow by having a return address refer to another function or subroutine. Also, it will be possible to jump back to a code previously introduced by the user input. Yeah, so that's what we're trying to do too. To understand how it works on the technical level, we need to become familiar with how the memory is divided and used. The debugger displays and names the individual instructions. The debugger can be used to detect such vulnerabilities. We can manipulate the memory. Another critical point is that the exploits usually only work for a specific version of the software and operating system. Therefore, we have to rebuild and reconfigure the target system to bring it to the same state. After that, this keeps clicking. I'll see if that helps. After that, the program we are investigating is called and analyzed. Most of the time, we will only have one attempt to exploit the program. If we miss opportunity to restart it with elevated privileges. So, let's see. I don't know what they're saying there. Odd. The memory. When the program is called, the sections are mapped to segments in the process. And the segments are loaded. I always want to rewrite stuff, you know. Fix bugs and text. Sorry. Can't be quiet about it. When the program is called, the sections are mapped to the segments in the process, and the segments are loaded into memory as described by the L file. So there's .text, .data, .bss, and you can stack in empty space. .text. The section contains the actual assembler instructions of the program. This area can be read only to prevent the program from accidentally modifying its instructions. So why does it say assembler? Has it the assembler stored in there? Or does it mean actually machine code? Or does this person think it's the same? I don't think so. Is it actually an assembler in there? I don't think so. Right? Let's continue. Any attempt to write to this area will inevitably result in a segmentation fault. The data section contains global and static variables that are explicitly initialized by the program. Yeah. So .bss. Several compilers and linkers use the BSS section as part of the data segment, which contains statically allocated variables represented exclusively by 0 bits. So, since I don't know what BSS really is, I need some other information here, right? Like, let's actually do ChatGPT again. Let's do, please explain .bss section of ELF file, right? So we're getting a better explanation than that, I'm thinking. So first, it stands for block started by symbol section. It's one of the sections in the ELF, which is used on Linux-like operating system. Purpose: the BSS section is used to declare variables that are uninitialized or initialized to 0. This sentence could have been there. I kind of guessed this might be it, but now we have it. It does not contain actual data in the ELF file itself, but rather indicates a region of memory that should be reserved for these variables when the program is loaded into memory. Size and storage. The BSS section does not take up space in the disk file because all variables in this section are initialized to 0. This is why BSS only occupies memory when program is loaded. The size of the BSS section is specified in the ELF file header, but the actual space is only allocated and zeroed out at runtime. Data type typically contains global and static variables that are uninitialized. Well, it kind of repeats itself, you know, so it's doing it. Is allocated and cleared set to 0 by the operating system when the program starts. This is why it doesn't need to store any data in the file. All the data in the BSS is initialized at runtime. Distinction from other areas. Data section. This section stores global and static variables that are initialized to non-zero values. Unlike BSS, the data section takes up space both in ELF file and in memory. Text section. This section contains the executable code of the program, including functions and instructions. Yeah, not assembler. This section contains read-only data such as string letters and constant variables. Consider following C code. We have an example with a global var, we have a global wall of 0. So these are uninitialized and a 0. And here too. So when the program is compiled, the compiler places in uninitialized variables into the BSS section. The BSS section is defined with size based on the amount of space needed for all uninitialized variables, but does not contain any data. During the linking process, the linker makes the BSS section in the final executable but does not include any data for it. Only the size and location are noted. Loading. When the executable is loaded into memory, the operating system loads or allocates space for the BSS section and initializes the space to 0. The 0 initialization is a key feature of the BSS section, ensuring that all variables in BSS start 0. So that's kind of like a thing then, right? Advantages. Efficiency. Makes the file smaller. So why would it not do that? Performance. Since operating system automatically zeroes out the BSS section, the program does not need to do this manually, simplifying initialization and reducing the time taken for such operations. Yeah, okay. Please explain well, I think I know the others. The possible other sections. 3 sentences for each. Oh, misspelled. Text section. The text section contains executable code of the program, including functions and instructions. It's typically marked as read-only and executable to prevent modification or accidental data corruption. This section is crucial for the program's functionality, as it defines the instructions for the CPU will execute. Data section. The data section stores global and static variables that are initialized to non-zero values. Unlike BSS section, which contains actual values that will be stored and will be loaded into memory when the program starts. It occupies space both in the L file and the memory during program execution. Raw data. Raw data section contains read-only data such as string letters and constant variables. Right. This section is marked as read-only, preventing the program from modifying its... Okay, so this is the difference between data, because this is variables, and this is static data, right? String literals and constant variables. So if we're printing, like, say, this is our data, colon, it will be here. If we have a variable initialized to hello, or your name here, and then you replace it with your name, then it's there. Init section. The init section contains initialization code that is executed before the main program starts, often used for constructors in C. Okay. This section is usually very small and runs only once when the program at the start of the program. So this is new to me, and this is very interesting. So init section contains initialization code that's executed before the main program starts. We have noticed that there are stuff before main, right? And of course there needs to be some setup too, right? This section is usually very small and run only once. After execution control is transferred to the main program, the section is typically no longer needed. Finite section. I haven't seen this. It contains termination code that runs after the main program finishes. I had to check, but I can't see. I have closed everything that's related to this on the color machine, so we can't test. I don't want to open it up again. The pizza will arrive soon. Similar to init, is executed once, usually for cleanup tasks before the program exits. It helps ensure resources are properly released and finalized, right? Used for destructors in C++, because destructors is an object orientation thing, so no C. .plt. Yes, I have heard of this, but I have not I don't know the details there. So the PLT, procedure linkage table section, is used for dynamic linking, particularly to resolve function calls to shared libraries at runtime. It contains stubs that jump to the actual address of external functions, allowing for late binding. Alright. Oh, got it now. This mechanism allows the program to refer to the resolution of function addresses until they are actually needed. So if we're running printf, it will be here, for example, right? GOT section. The GOT global offset table section works alongside the PLT section to facilitate dynamic linking. Okay. It holds addresses of global variables and functions that may be resolved dynamically at runtime. The GOT helps the position-independent code pick, making the program more flexible and secure. Okay, so this might be just for this then. Why would it be needed else? I don't know. Because we already have this? What kind of global variable would this be? Something, I guess, more base that's in the system, I guess. Yeah, of course there are variables. I'm mostly like thinking functions, but it's other data do. SymTab section. The SymTab symbol table section contains a list of all symbols, functions, variables. Yeah, we've listed this, all the symbols. Function variables in the program, including their addresses. This is mainly used by debuggers and linkers to resolve symbol names into addresses. This section is usually not present in stripped binaries, as it increases the file size. Okay. str tab, string table. Alright, section stores strings used by the symbol table, particularly the names of symbols. It stores a reference to strings in other sections like SymTab and DINSym. This section is essential for mapping symbols to the human-readable names during debugging and linking. Okay, so if we like save debug information, will that be where it is saved then? I'm feeling stupid. I don't know. We'll see. But we'll have to research more stuff. The dynamic section contains information about the dynamic linker to manage shared libraries. It includes entries for dynamic linking such as paths to shared libraries and relocation information. This section is crucial for programs that rely on dynamic libraries to function correctly. Rela sections. These sections hold relocation information used to adjust addresses in the program when it's loaded into memory. Rel is used for simple relocations, while rel includes additional fields for edits. These sections are essential for dynamically linked executables, allowing them to properly reference shared libraries. Okay. So, the DINSym section is a symbol table used specifically for dynamic linking. Yeah, so I'm kind of thinking my voice is dying on me. LSTTS, the lost ones.
12.dynSym section. The .dynSym section is a symbol table used specifically for dynamic linking. It contains symbols that are needed for resolving function calls to shared libraries at runtime. Unlike .symtab, it only includes symbols necessary for dynamic linking, making it more compact. 13.interp section. The .interp section contains the path to the dynamic linker, like /lib/ld-linux.so.2, which is used to load shared libraries. This section is present in dynamically linked executables and directs the operating system to the appropriate interpreter. It is one of the first sections to be processed during program loading. 14.note section. The .note section stores additional information such as build attributes or versioning details. It is often used for storing metadata about the ELF file, including details about the target architecture or ABI. These notes are not directly used by the program but can be valuable for tools and utilities. 15. Debug sections. Sections like .debug_info, .debug_line, and .debug_str store debugging information generated by the compiler. They include data about source code mappings, variable locations, and other details useful for debugging. These sections are usually stripped from the final binary to reduce size unless debugging is required.
Yeah, so here is the debug info. So I can't read more today. Sorry. Where did it go? Oh, so we opened two articles, so it hopped over here. Yeah. So just added more info in the middle there. The heap. Can I read aloud? That is. The heap is allocated from this area. The heap memory is allocated from this area. This area starts at the end of the BSS segment and grows to the higher memory addresses. The stack. Stack memory. Let's TTS. Sorry.
The stack. Stack memory is a last-in first-out data structure in which the return addresses, parameters, and, depending on the compiler options, frame pointers are stored. C/C++ local variables are stored here, and you can even copy code to the stack. The stack is a defined area in RAM. The linker reserves this area and usually places the stack in RAM's lower area above the global and static variables. The contents are accessed via the stack pointer, set to the upper end of the stack during initialization.
Yeah, so
during execution, the allocated part of the stack grows down to the lower memory addresses.
Here
Modern memory protections.
I'm calculating 4 hours of film. The food will arrive soon. So if I go and prepare now for the movie, we can get started when the food arrives. But probably not anyway for my kids, right? But it's time.